This is Riemann's zeta function, and since its publication in 1859, it has stumped mathematicians, making it one of the most famous unsolved problems in the history of math. Well, before we dive deeper, let's talk about prime numbers.
First of all, a prime is a number whose only factors are 1 and itself. For example, numbers like 2 and 3. Modern prime number theory focuses on estimating unknown primes by finding the pattern in the spacing between consecutive primes. In 1796, a mathematician named Carl Friedrich Gauss calculated up to 3 million primes and plotted them on a graph. This graph is the prime counting function. Its y value increased by 1 every time x was a prime number. When expanding the scale of this graph, Gauss realized that it started to resemble a function with the slope of x over the natural log of x. He outlined this similarity in his prime number theorem. Later, mathematicians found a closer approximation to Gauss's function, the logarithmic integral function. Now that we know about primes, let's cover the zeta function. A zeta function is a harmonic series, which means it has infinite solutions or diverges when s is less than or equal to 1. Using this function and expanding it to the imaginary number realm, Riemann created a zeta function that included complex numbers. When graphing this function, Riemann noticed an interesting phenomenon. There seemed to be infinite zeros when the real part of s was 1/2. He called these non-trivial zeros. This relationship is basically Riemann's hypothesis. So what does all this have to do with prime numbers? By adding his non-trivial zeros to the logarithmic integral function, Riemann was able to create a function that perfectly resembles Gauss's prime counting function. This is Riemann's prime counting function, and unlike Gauss's function, it allows mathematicians to estimate large unknown primes to near perfection.
So why should we care about Riemann's hypothesis? Well, Riemann's hypothesis has major consequences in quantum mechanics. Recent studies have shown that the spacing between prime numbers, as shown in Riemann's function, corresponds to the spacing between consecutive atomic energy levels. As a result, Riemann's hypothesis and prime numbers may hold a key to understanding how quantum particles interact, leading to significant breakthroughs in biology, astrophysics, and numerous others. Thank you for watching.